Hey guys. Not in the right place. Okay. So a few things for today. I would like for everybody to attempt the honor lock practice quiz. Today. So it's important that you go through that process because we want to work out any bugs or issues with honor lock before the test. So remember, exam 3 is this Friday during class time. So instead of coming to a Zoom meeting on Friday, you're going to go to Canvas. You're going to click on exam 3. It will prompt you to allow honor lock to run. And then once you're in the Canvas assignment, there will be a link to take you over to my math lab. But you have to go through Canvas because it's an honor lock thing. So go to Canvas, try the honor lock practice quiz, and then on Friday during our normal class time, instead of joining the Zoom meeting, you're going to go into Canvas, you're going to click on exam 3. It will prompt you to open honor lock or to let honor lock run. Then it will take you over to MML, where you'll actually complete the test. Somewhere in between those two, like after you open the thing in Canvas, but before it takes you to MML, you're going to be asked for a token. You're going to be asked for some form of payment to honor lock for their services. In place of you giving them a credit card or you giving them some other sort of payment, you're going to give them a little code called a token, which I will email each of you individually. So everybody's going to have their own token, their own special code. I got them. I requested them last week, got them yesterday. So I have a code for each of you to take the test. But it's important that you check your email just before class. Okay. So you're going to start in Canvas. Click on the test. Allow honor lock to run. Input your token. Which will come from my email when prompted. And then you'll be taken to MML for the test. Okay, so that's how it's going to run. Those are going to be the mechanics. I want to make sure everybody runs through the honor lock practice quiz before Friday. So if you run into any problems with honor lock, we can get them fixed and sorted out before the test itself. I see that there's still only a few folks in here. But do any of you guys have any questions about that? Okay. Then the intent was, or it still is, for the rest of today to be review for you guys. So what homework questions or what problems would you guys like to play with? What would you like to look at?
How far back is the exam going back to homework 21, back to which one?
Back to homework 16. Homework 16 through, actually, let me see if I'm remembering that number right. So we talked about it at the end of last time, the start of last time, 14. 14 through 21.
Okay.
So it's chapter 5, right? 5.1 was like operations with functions and combining functions. Everything from there through what we've just done will be on the test. Other questions about the test, how it's going to run, that sort of stuff? Okay, then what would we like to do? What problems would we like to solve? How would we like to review for our test?
Is it possible we could go through, like, I guess some of the formulas that were given in each of the I guess homeworks, just as like a review?
If you look at the video from not yesterday, from Monday, I did post a video that has all the formula in them, but yeah, sure. So you've got the definition of an exponential function. It's one constant times another constant raised to your variable. Here, c is the initial value, and a is called the base, also sometimes called the growth or decay factor. And then we have the rate formula. This is if you have something growing by R% per year or decreasing by R% per week, something like that. That's C times 1 plus or minus R to the X. R here is called the growth or decay rate. And we use the plus if we're growing, and we use the minus if we're decaying. We have the half-life formula, which is C times 1/2 to the, we usually use the variable t here to represent time, t over k. Here k is called the half-life. And then we have the doubling time formula, which is the same sort of thing, just with a 2 instead of a 1/2. Here k is called the doubling time. And then we have the compound interest formula. Here P is the principal. P is the same thing as C in all of these previous formulas. It's the initial value or the original amount. R is the interest rate, sometimes called the nominal interest rate. And N is the number of compoundings per unit time. So, oh, and there was one more. We had the continuous growth rate formula. So this is used for continuously compounded interest. P is again the principal. And R here is called the continuous growth rate. So if you have continuously compounded interest or a problem that talks about a quantity growing or decaying at the continuous rate of R, then you would use this. If you're talking about compound interest, regular compound interest, you would use this. If you have something that doubles every so often, you start with 300 bacteria and they double every 15 hours, then you would use this formula. If you have a half-life problem, something that gets cut in half every so often and starts with C, so you've got like maybe C grams of some material and it decays by half every 2,000 years, then you would use this formula. This guy is for something that is increasing by a given percent per unit time. So if something is something's value is increasing by 10% per year or decreasing by 5% per week, then you would use this guy. And then this is just the definition of an exponential function. And all of these can be put into this form. If you're looking for a growth factor or a decay factor, you need to put your function into this form. And then also it never hurts to remember that the growth or decay rate which is the same as the effective interest rate in these interest problems, can be calculated as the absolute value of A minus 1. Those were all the formulas from 5.3 that we needed. So I see there's something going on in the chat here. Is there a problem that uses everything we've learned? All those formulas going to be on the exam. I could ask you a question. Yeah, any of these formulas. So for the exam, you do need to know these formulas, right? These formulas, your knowledge of them is fair game to test on the exam. The important things are the concepts, making sure that you're comfortable with the algebraic manipulations and stuff like that. But yeah, these formulas are all things that you'll need to know for the exam. The intent is that these will stick in your brain after going through the homework, right? So having done all the homework problems that require you to use these formulas, they should be familiar and they should be sticking in your head. If they haven't done, then you should make some flashcards or something like that. Austin asked if there was a problem that we could do that uses everything we've learned. Not quite, because there's really quite a lot of stuff here. So we could solve some problems having to do with exponential functions and logarithms. We could reach back and do some 5.1, 5.2 stuff about combining functions. But give me a little more specific idea. What sort of thing would we like to do? Exponentials, logs, equations, simplification, something older, something like finding f plus g and its domain, or f of g and its domain. What would we like to do? Something exponential. Okay. Let's look at something like this. Say that the value of, let's say the value of a certain stock is currently $250 per share, and it's increasing by 3% per day. I might ask, how long until the value reaches $300 per share. So this involves a little bit of modeling and also a little bit of solving exponential equations using logarithms. Mesa asked about project 3. Yeah, I haven't posted that. I don't actually, so that stuff is all saved on my work computer, but I should be able to suck it out through the cloud. So I will go ahead and post a project 3 for you guys to play with. Let me give myself a reminder to do that right now. And then I'll give some extra time for the project. You won't have to hand that in right away with the test, but just so you can have some extra practice. Yeah, where the hell is this? Come on. While I'm digging this up, can anybody tell me which of those formulas am I going to use to build my model here? Formulas. What is this? Oh, that's nice. Pokemon activities. Project 3, right? Save this. Yeah, here we go. So I found a copy of an old project 3 of mine that I will post for you guys. There. All right. So coming back to this. Which of those formulas am I going to use to build the model that I need to solve this problem? Is this a compound interest thing? Is it a half-life thing? Is it a doubling time thing? What is it? Yeah, I was given a growth rate, right? I was told that the value of the stock is increasing by 3% per day. So that's a growth rate thing. So I think we've just been calling that our rate formula. F of x is c times 1 plus r to the x. And because the value of the stock is increasing, not decreasing, I'm going to use the plus rather than the minus. If the value of the stock was decreasing, then I would use the minus. Here, c is the initial value. So right now, the value of the stock is $250 per share. So c is 250, and r is my growth rate. 3%, and 3% as a decimal is 0.03. So if I plug those things into this formula, I get f of x equals 250 times 1 plus 0.03 to the x, which I can simplify a little bit. The 250 can't come into the parentheses because that stuff is all being raised to the x, but 1 plus 0.03 is 1.03. So that is the function that tells me the value of my stock x days from today. So if all the problem asked for was a function that models the value of the stock, I would be done. But that's not what the problem asked for. The problem asked, when will the value of the stock be $300 per share? So what should I do with this thing in order to figure that out?
Do you have to put the whole equation equals to 300?
Yeah, perfect, right? This is the value of the stock after X days. I want to know when will that thing be equal to 300. So I need to solve the equation 300 equals 250 times 1.03 to the X. And then what would be a good first step in solving this equation?
Divide by 250?
Good. So that gives me this. And then both of these numbers are divisible by 50, right? So I can cancel a factor of 50 here. 300 is 6 times 50. 250 is 5 times 50. So this is 6/5 equals 1.03 to the X. And then from here, what should I do?
Take the log of both sides.
Good, yeah. To solve this exponential equation, which has a variable trapped up there in the exponent, I need to take logs. And it's up to me which logarithm I want to take. I could take the base 10 log, the log log, or I could take the ln of both sides. We've been using the ln a lot, so let me go ahead and use the base 10 log this time. So I'm going to continue this up here. I would get log of 6/5 equals log of 1.03 to the X. The left-hand side, nothing's going to happen here, but over here, this log of some number to the X is the same as X times the log of that number. That's one of our properties of logarithms. Powers inside are the same as multiples outside. And so finally, to finish, we divide both sides by this number, the log of 1.03. So I get log of 6/5 divided by log of 1.03 equals X. Now, is there anything I can do to simplify that? Is there anything here that can be combined or canceled? Can I cancel the logs?
No, you have to put it in the calculator.
Right, yeah, so this is function notation, right? Not multiplication. So to simplify from here, just like Mesa said, the move is going to be to use the calculator. So I'll pull up my virtual TI-83. You guys can follow along. Let's do it like this, so you can see everything at once. So if I want to know about how big this number is, I'm going to come in here and type log 6/5, close that parentheses, and then divide by the log of 1.03. This gives me about 6.17. And that's 6.17 what? What is X measuring here? How would we know?
It's days.
Yeah, it's days, right? So remember, because they told us that the price of the share is increasing at 3% per day, I'm measuring time in this equation, in this function, by days. So X here is measuring time in days. This is the value of the stock after X days. So this is how many days it will take for the value of that stock to reach $300 per share. Stocks don't actually behave like this, right? At least not normally. I'm not aware of any stocks that just grow exponentially. But sometimes they behave like this for a short period of time and then they change. So if you were following what was going on in the market and you were watching this stock, now would be a good time to buy this guy because you know he's going to go up. In fact, you know he's going to go up from 250 a share to 300 a share in 6 days. So the interpretation is just as important as the algebra. Any questions, though, about how we knew to use this formula, how we knew to plug these things in, or where this simplified form came from? Okay, then. I would like to think back a little bit to 5.1 and 5.2. Just make sure that we're comfy with some of those concepts. You could say something like, if f of x is 3 to the x, then f inverse of x is log base 3 of x. Use the info, let's say like this. Since 0, 1, 1, 3, and 2, 9 are on the graph of f of x, what points must be on the graph of f inverse of x? So here we're given a little bit more information than we need to solve the problem, but I'm wondering if we remember the connection between points on the graph of f and points on the graph of f inverse. So let's start with 0, 1. Since 0, 1 is on the graph of f, what point is on the graph of f inverse? Yeah, very good. One of you sent me the correct trio of points there. So remember, f inverse, to find, if you're given a point that's on the graph of f, to find a point that's on the graph of f inverse, you flip these guys over. This says f sends 0 to 1. That means f inverse has to send 1 back home to 0. And similarly, (3, 1 and 9, 2 are on the graph of f inverse of x. And you could check that the base 3 log of 3 is 1, that the base 3 log of 9 is 2, that this all works out. So I could have omitted this bit of information at the top and just said, if 0, 1, 1, 3, and 2, 9 are on the graph of f, what points must be on the graph of f inverse? And we could still come up with 1, 0, 3, 1, and 9, 2. We can extend this a little bit. The domain of f of x equals e to the x is all real numbers, negative infinity to infinity. And the range of f of x equals e to the x is 0 to infinity. What is the domain of the inverse function f inverse of x equals ln of x? Okay. So remember, the idea here is that the graph of f inverse, if AB is on the graph of f, then B comma A is on the graph of f inverse, which means everything that's in the domain for f is in the range for f inverse, and everything that's in the range for f is in the domain for f inverse. So what is the domain of the inverse function here? This is one of those problems that you could attack in multiple ways. You could go ahead and graph the natural log of x and try to tell me what the domain is from the graph. If you don't see how to do it from this, go ahead and do that right now. I'll do it here along with you. What do we think?
So would the domain be 0 to infinity?
Good. Yeah, the domain of f inverse is the same as the range of f. So the domain of this function is the same as the range of f, which is, yeah, the open interval 0 to infinity. What about the range of the natural log? And again, you could look at the graph, or you can think about the relationship between f and f inverse here. Ideally, we should be comfortable doing both. I could ask you this question in either setting. The range of f inverse, remember, is equal to the domain of f. So what is the range of the natural log? It should be the same as the domain of e to the x, right? And that's, yeah, negative infinity to infinity. So this 5.1 and 5.2 stuff was a little while ago, and I know we've been working very hard with the exponentials and logs and solving equations and getting in with the nuts and bolts. But make sure you remember this stuff too. I can give you one more kind of like this. Right, so here I give a formula for f of x and a table for g of x. I could ask you if either of these functions are one-to-one. I could ask you to find the inverse of either of these functions. But instead, let's say let's say f of g of 0 and f minus g of 1 and f of g inverse of 7. So let's start at the first one there. How would I find f of g of 0? Anybody remember how these things work?
Is that a 6 or a 0 on the?
This last row here is a 0, and this is a 0 here. So the trick for all of these guys is to start off with the definition, right? F of g of 0, that's f of g of 0, like this. So I'm looking for f of something. In order to proceed, I have to know what that something is. That something is g of 0. So I need to figure out what is this inside. So g of 0 is going to be a number, and it's a number that I can get from the table for g. What is g of 0? What's the thing that's going to go in the parentheses on the far right?
3.
Yeah, right? G of 0 is 3. So f of g of 0 is the same as f of 3. And then to figure out f of 3, I look up here to the formula for f of x. This is 3 times 3 minus 1 is 9 minus 1 is 8. So f of g of 0 is 8. Did everybody follow that? Right. There will be something on the test which examines your comfort with these concepts and notation. The test is going to focus on exponentials and logs, but there will be something on this test that makes sure that you've learned and are comfortable with the function notation stuff from 5.1 and 5.2. How would I get started with this second part? What's the kind of, get started step? Like here we wrote down the definition of f of g of 0. What would be the definition of f minus g of 1?
You have to put in 1 on the f of x and find the g of 1.
Yeah, exactly, right? So I need to figure out what f minus g of 1 is in terms of f of 1 and g of 1. And f minus g of 1 is f of 1 minus g of 1. That's the definition. So yeah, so now I figure out what is f of 1 and what is g of 1. G of 1 I can get from the table is 7. F of 1 I can get from the formula for f of x. It's 3 times 1 minus 1, which is 3 minus 1 is 2. So this is 2 minus 7, or negative 5. Questions about this? Okay, then how about this last guy? What is my get started step here? What is the definition of f of g inverse of 7? Oh, that's nice. Well, just like this first guy, f circ g of 0, f of g of 0 This guy is f of g inverse of 7. So everybody follow that step. It's this first step that kind of makes things go, right? Once you have this definition step written down, you just kind of have to follow your nose. But we do have to remember these definitions. So then from here, I say, okay, this is f of something, but what is this? What is the inside here? What is g inverse of 7? Who can help me with that? In words, what is g inverse of 7? Well, let's look up here. G of 1 is equal to 7. So g sends 1 to 7. G inverse is the function that exactly undoes g. So g inverse is going to send 7 back to 1. In other words, g inverse of 7 is 1. So this is f of 1. And then f of x is the function that multiplies by 3 and then subtracts 1. So this is 3 times 1 minus 1. Just 3 minus 1 is 2. So I know it's been a little while since we've played around with these things. You may want to go back and review some of the material from 5.1 and 5.2. There were 2 homeworks there and a quiz. And if you haven't looked at those in a while, I suggest doing so. They are open. I opened everything from homework 14 through 21 for you guys to practice before the test. So if those things are feeling rusty, if these things aren't coming to your mind as I ask them, please do yourself the favor and go back and take a look. Okay. I think we have time for one more. What would we like to do?
Oh, yesterday I went over the homework and I kind of forgot how to plug in those functions in a graph, and like if they ask questions about the graph, like I forgot some of those stuff.
So like one of those, like solving the equation using the graph, like estimate the age of the fossil graphically, that sort of thing?
Yeah.
All right, so let's say a fossil, what's the right way to say this? So the half-life of uranium-238 is about 7,200 years. If a bomb is dropped irradiating the area where the bomb detonates, with U-238, how long will it take for there to be only 10% of the original radiation? So this is similar to those problems in the sense that it's a half-life problem, one, and also you're not given the starting value. You're not given the amount of radiation immediately after the bomb drops. You're just given the half-life of the substance, and you're asked when will you get to 10% of the original. So we would start with our half-life formula, F of t equals c times 1/2 raised to the t over k. I don't know what c is, but I do know what k is, 7,200. And if I want to know when will we get to 10%, that's 10% of C, whatever C is, which is 0.1 times C. So the equation I need to solve is 0.1 C equals C times 1/2 to the T over 7,200. I can begin by dividing both sides by C, and I get 0.1 equals 1/2 to the T over 7,200. And this is an equation I could solve with logarithms now. I could take the natural log of both sides and then fiddle around with that. But if we're wondering how would we solve this graphically, or how would we estimate a solution graphically, we would come in here to our calculator and type in y1 for one of these and y2 for the other. So I'll type 0.1 for y1, and I'll type parentheses 1/2 raised to the parentheses x over 7,200 for the other. And I can try to look at the graph, but they're both going to look like straight lines right now. So in order to get an idea for where these intersect, I need to pick a reasonable window size and a reasonable scale. The half-life of this stuff is 7,200 years, and I'm asking when we get down to 10%, so that's way less than half. So I'm going to set this to something crazy, like 70,000 for my, I'll set my x min to 0, and my x max to something crazy, like 70,000. My y min 0 is fine, because I'm talking about percentages. I'll never have a negative amount here, and my y max could be 1. And I'll set my y scale to something like 0.01, so I can look at a really fine picture here. All right, so that x max is too large. Whoop. So let's change this to maybe 30,000. Ah, that's looking pretty good. So remember, what I want is the location of this intersection point. I can grab my trace function, hop up to that graph, and start looking here. I'm looking for the y value to be exactly 0.1. That's where these are going to touch. We're getting closer and closer and closer and closer and closer. Oh, that's too far. So here, look. When x is 23,617, we're awful close. So if I want to really refine my guess, I'm going to set up a table where the x values start at 23617, and I'll take very small step sizes. 23617. And I'll take a step size of maybe 0.001. And then I will look at my table. I'm looking for a place where y2 is exactly equal to y1. And as I come down here, I'm going to see the y2s start to fall. Oh, I need to take bigger step sizes, sorry. Let's take step sizes of 0. Oh, yeah, this is give me an extra 0, 0.001. All right, that should go a little quicker.
What was your y max for that in the calculator?
I used the y max of 1. Oh, this keeps setting back to that, so 0.01. Let's try this. Yeah, I used a y min of 0 and a y max of 1. So as I scroll down here now, y2 still not really changing fast enough for me. Play around with these table settings. Say just 0.1. All right, there we're getting somewhere. And you can scroll down here until this y2 gets as close as possible to 0.1000. It would take a while, and how much accuracy you need depends on what the problem specifies. If you just want one decimal place of accuracy, then I would be happy or if you just wanted like the nearest integer, I would be happy with our first guess. But if we need to get closer still, we just keep scrolling until we get down to a place where y2 here is very, very close to 0.100. Now, on the test, I would never ask you to do anything like this because you have logarithms. So while this is a meaningful step along the way to learning these things, the right way to solve a problem like this from here would be to take logs on both sides, because you can get the exact answer very quickly like that. I take the natural log of both sides, then I get the ln of 0.1 equals this whole power here can come down front as a multiple. So I'd have t over 7200 times the ln of 1/2. And this is now an equation I can solve. Start by multiplying both sides by 7200. And then divide both sides by the ln of 1/2. And that gives me t. So we can see, we can see exactly what that answer would have been by entering this number into our calculator. That's 7200 times the natural log of 0.1, and then I divide by the natural log of 1/2. And this is what I find. So while I recognize that those, estimate the age graphically problems were meaningful back in section 5.3 before we had the tools of logarithms, they're not especially meaningful anymore because now we can solve those equations algebraically. I can promise you I will not put a graphically estimate the age of the fossil type problem on this test. I may give you a problem like this where I ask you to tell me how long until the how old is the fossil, and then solve with the logarithms, or how long until there's 10% of the original amount and solve with logarithms. But I wouldn't have you estimate one of them graphically. I don't think that is a good use of your time. The purpose of having you do those problems back then was to show you that there are these equations that we can't solve any other way yet, so that later when we introduce logarithms, you'll recognize why they're important, why they're valuable. That is all we have time for today, so I'm going to have to stop it there. If you have other questions, please send me a Canvas message or an email. If you decide to email me, please include the course and section number that you're in. You're in MAC1105, section 005. Or come by my office hour. I have an office hour from 9 to 11 tomorrow, 9 a.m. to 11 a.m. And it's the same link all through the semester. It's right there on the Canvas page, on our home page in Canvas. It's also on the syllabus page there. So please continue to review and work hard getting ready for this test. Please take the practice quiz. The practice quiz in Canvas for you to test honor lock is important. If you don't do that, you may run into tech issues on the day of the test, and that could end up eating up some of your test time. I don't want that to happen to anybody. If you don't have access to a working webcam for the purposes of the test, please let me know so I can contact the honor lock people and figure out some other way either to build in an exception for you in honor lock or some other way for you to be proctored that day. All right, any questions, guys? Okay, I'm gonna go ahead and stop the meeting here then because I have another class that starts at 11. Like I said, if you have any questions, don't be shy about reaching out to me. Canvas messages are the best way. But whatever you're comfy with works for me. You can also use the Ask My Instructor button on Pearson if you run into something while you're reviewing. And if there's anything that you'd like to talk about at length, please come by my office hour meeting tomorrow between 9 and 11.